All right. Today I would like to talk about the general two-body problem. With general, I mean the two masses might be almost the same. At least, I mean that the smaller mass might not be so small after all. Like the approximations we usually do, that one mass is much, much smaller than the larger mass. Like a planet in the solar system. So this is more of an exact result in Newtonian mechanics. And what we are going to show is that the mechanical energy, the total energy of the two-body problem, equal this formula here, where the mass is capital M and M, and divided by something called the major axis. If we look at a general closed orbit solution to the Newton's equations, we get ellipses or a circle, but that's just a special case of an ellipse. So the major axis, this distance here to this distance here, is called 2a. That's the major axis. And A is what people usually are talking about, and that's called the semi-major axis. And it's just the half of the major axis, so A. So this is a characteristic for elliptic orbit. So you have this distance 2a, and you also have a distance here 2b, which we're not going to talk about here. So in order to solve this problem, we don't want to treat both of the planets or particles individually. We want to replace the two-body problem with a one-body problem. This we can do if we introduce one fixed mass, the sum of the masses, which we place in the origin, m plus m, and this is fixed. And then we introduce another mass, the reduced mass, μ, with the red sign here, reduced. And this is the one then that is moving around in an elliptic orbit. And it's also the case that the fixed mass is placed in something we call the center of mass, or center of gravity. That's why it's called usually G, that point, center of gravity. But center of mass is the normal word for it. So instead of two particles moving around each other, we only have one. So that should simplify things, hopefully. And I want to introduce some properties here. For example, if you look at this orbit here, then there is a distance here, which is rather large, isn't it? And if you look here, it's a smaller distance here, distance r. And the distances here from the center of mass, from this fixed point, to the reduced mass. It's given here from the original problem. There are two distances, but as you can see, it's just a distance between particle 1 and particle 2, or if you like, between m and capital M. So that's the distance between, or if you're there, still distance between the two particles. And then you can see here that there is a maximum distance here and a minimum distance here. And we can immediately see here that this one, this distance, minimum distance plus the maximum distance, that is just 2a, isn't it? And if you like, yeah, then we can solve for A. So we divide by 2. So this is the property of the so-called semimajor axis. And the distances are relative distances, relative orbit, the distance between the particles, and also the velocity of the reduced mass is simply the relative velocity. What do we have here? Yeah, you have the velocity of particle 2 relative to particle 1. So from the particle 1's perspective, 2 has a certain velocity. And then we just look at the speed. So take the modulus of that. So this is the speed, v. And I will also give you a general formula for the speed in an ellipse. It's given by this formula here. And it's common to introduce a parameter μ equal the gravitational constant times the total mass. So this is not the reduced mass, it's just a parameter for this. And also for elliptic orbits, we are normally talking about an eccentricity, and that is how elongated the orbit is. For example, if E, as you see here, if it's 1, then rmax equal 2. So in that case, the orbit is like this. And this is two-way. So it's very elongated in that case. And one can express it, the maximum distance is a times 1 plus e, and the minimum distance a times 1 minus e. And e is always less than 1 for a closed orbit, like an ellipse. And you have the special case when e equals 0, it's a circle. Then you see rmax equal a and rmin equal a2, as it should be. The radius is constant for a circle. Okay, so let us show now what the total orbital energy for any closed orbit might be. And this is the problem that we're going to show, that is just a very, very simple formula for any closed orbit. So if we remember mechanical energy, we realize that it's a sum of the kinetic energy, and in this case, the kinetic energy is, here is one particle moving with a certain speed, right? And the fixed particle here is not moving at all, so there is no kinetic energy of this particle, only that one. So this is 1/2 times the mass, which is the reduced mass, times the velocity squared. And then there is a potential energy, and then it's g times one mass times the other mass divided by r, and it's also a negative sign. And it comes from the Newton's gravitational law, and the negative gradient of that is, the gradient of the potential energy equal Newton's force, and then you get this. So, and this we call μ, gm plus m. So you now have this formula here, 1/2 the reduced mass times some kind of expression here, right? V square, and that I gave you here. V square equal μ times 2 over r minus 1 over a. And I'm also inserting a convenient value. I mean, this mechanical energy is a constant for any r value. So I just pick one. Let's say R equal the maximum value, A times 1 plus E. So I inserted that over here. And then here is the gravitational potential energy. So you have minus mu, and then the reduced mass, yeah, right, and then over R, which is the maximum R in my example, A times 1 plus E. So you have it here. And then let's see if we can simplify. This times this will be this term, and this times that will be that term, and then this is what it is, right? And then that term and that term cancel perfectly. So what we're left with is this. And then we just introduce reduced mass, the definition of that, mn over the total mass, mu, that was just the parameter g times the total mass, 2a, and then we get the final result, gmm over 2a, which we were supposed to show for any closed orbit. And any closed orbit in a gravitational problem is an elliptic orbit, with a special case of circular orbit. So we have succeeded. So this is always true, this result here, for a closed orbit, a bound system. So let's just for fun take a look for special case, a circular orbit. So in that case, you have the total mass, a fixed point in the center, and the reduced mass is circling in a circular orbit. And again, the major axis is 2a, so the radius of the circle must be a. And let's use the second law, Newton's second law. Force equal mass times acceleration for one particle, in this case the reduced mass particle. And Newton's second gravitational law says, okay, it should be g times that mass, okay, divided by the distance squared. And the minus sign is, I introduced that because the force is in this direction, to the left. And then it should be the mass times the acceleration, centripetal acceleration, and also that acceleration is in that direction, to the left. So, okay, then it's a minus sign here. Yeah, and then from this result here, we can find the squared velocity equal this. And these things here are exact results. And, okay, we look at the energy. Here's the kinetic energy, and here's the potential energy. And v squared, okay, that's that. Okay, so we get this. And we still have this. And those are rather similar terms. So we get this. And then I introduce the reduced mass here, like this. This is still g m plus m divided by r, but that is the semimajor axis A. So let's insert that one. And now those masses here cancel, and you get this final result again, minus gmm over 2a. So it's true for elliptic orbits and also circular orbits. So that's an interesting property that is good to remember. Thank you very much. See you later.